So imagine you have like a 100-page long document with one small mistake inside of it, and it's like buried somewhere inside of the document. So when you're using an RLM, it searches through the document, it finds like what it believes could be the answer or a possible answer. It carries it through its working state, and eventually it returns an answer. And it's very much possible that the final answer can be influenced by that one mistake. And that mistake can be something simple like a note, maybe your PDF tables are not showing correctly. Basically something that belongs inside of the paper, not necessarily an attack. So in the next 20 minutes, I'll be talking about what happens when that happens and what the trajectory of the RLM shows us about that failure. So again, my name is Kevork Sulahyan, and this talk presents a kind of small but event-driven study of source trust in recursive language model trajectories. The motivating question that made me start this research was simple. So when an RLM works over a long document, what happens when the local plausible source span is wrong? For a single style system like a base LLM, or even like a RAG system we have, when the retrieved context is incorrect, that changes the answer. With RLMs, that creates a longer path because it searches, stores intermediate results, makes some assumptions, may call like helper functions that you can provide to it, call submodels, and then proceeds to create the final answer. So a mistake can span it like at one stage and go through all of the stages until the end where it generates the final answer. So the claim I will defend is kind of narrow, which is source local errors can become answer evidence inside RLM trajectories. So first, I'll also explain, what RLM is as an abstraction. Then, what capabilities test that we are planning to publish, and describe the benchmark that we're using, the attacks, and work through like a trace level examples that we have found for now, and close with the results and possible next steps. All right. So, standard LLM, it receives the prompt, it has a document, it puts everything in its context, and then produces an answer based on that. RLM handles a large source a little bit differently. You can think of it, searches or thinks of it like a student or a researcher, which has like an access to a library. So first it does its research, and then it decides what to investigate next based on what it's learning. This entire process is coordinated what they call a root model or a base model. And this base model, manages everything from start to the end. So it decides what to search for, which passages to read, what information to keep in the working state, whether to call helper functions, and it also decides when it has enough evidence to create the final answer. So the diagram on the right, while it's kind of simple, it shows like the entire loop that's happening. So the input, search, then there's like a loop within the working state, and then the search. So it like does it a couple of times. You can limit how many times it does that, and then it generates the final answer. So again, if you haven't heard about RLMs, it usually begins like an LLM with a system prompt. But in this case, the entire document is given to the model through its Python REPL environment. So it never puts everything inside of its full context. And these things can be not just like large PDF files, but it can be a collection of documents. And more people are using it to go through large code bases because you can't memorize everything if it has too many lines. So the root model searches through the source. It retrieves local passages, and it reads the passage and then updates its working state. The working state is similar to your own personal notebook, so it can have partial answers, open questions, maybe contradicting claims, and you can also write your possible next steps. And then the model analyzes this notebook and to decide what to search for next. So it may follow a reference, investigate something new, maybe go outside of the documents if you give it the right access, of course. And investigate the conflicting claims or ask a helper model to summarize or analyze a document that is too large for the LLM to put into its context. And the cycle continues until the root model decides it has enough evidence to answer or create the final solution. So this makes RLMs very useful for long and complex sources because they're dividing a broad question into smaller parts and then focus attention on what it believes to be the most important thing here. It also means that the final answer depends on the entire trajectory of the evidence decisions that it's making. So again, a misleading passage may enter during a search, incorrect interpretation may be stored in the working state, and a helper model, for example, especially if it's not like an LLM or maybe something very small, it could make an incorrect claim, and conflicting evidences may appear that confuses the root model when trying to select the final decision or final answer. So this is what I mean by trajectory source trust. So you have to trust what's happening in every single steps, which kind of makes the next question of this research obvious. So which sources entered the trajectory? How did the system interpret them? And which ones ultimately led to the final answer, especially if it's a mistake? You have to follow everything. So obviously answering that question requires a record full process, and we log what the system searched for, what it read, what it retained, which helper model was asked, and the same loop again repeats for the loop of, let's say, collecting documents or information repeats for the helper models, and of course what the model finally submits as an answer. So this kind of sounds similar if you have used like large coding agents or I guess bigger RAG systems, and even in those when there's the retrieved document has a poison in it, then it may be retrieved and used in the final answer. In the RLM, the information can persist again across several rounds of research, summarization, and reasoning, but we have more detailed steps of what's happening point by point, because that creates more opportunities for an answer to spread through the system. It also gives us a richer evidence of what's happening in our systems and how we can explain or interpret the results. Okay, before I discuss the attacks, I just want to talk about what we did or doing to check if this is even viable to do as a research. And the first thing we did was the capability check. Here we tested the model against a benchmark called long bench versus 2. There are a lot of safety benchmarks, but I don't think they suit RLM specifically because it works best when the context is insanely large. So using this one, we tested just against the normal benchmark, which is like an multiple choice questions. We tested the model against LLMs that can have up to 1 million context availability. RAG systems, the DSP-based agentic loops, I forgot their name. And it kind of gave us acceptable results. And the second thing that we tested was the safety metrics, which is where we turned this same long bench dataset into a safety benchmark by putting the poisons inside of the documents. And we call this the copy ASR, attack success rate. But I think of it more as an injected claim adoption because whether the final answer adopts the poisoned results is important, but it's irrelevant as long as it's like somewhere in the middle. If it's accepted in the middle, then we see this as a possible failure. And then the third one is the diagnostics and the extra helper functions, let's call them. So this include control variants, root code reminders, schema checks, source reader logging, and other bounded probes. This is basically to help us explain what's happening and why, and it helps us kind of interpret the results, which you're going to see in a couple of slides. Oh, sorry. Oh, here we go. So yeah, the number of our attacks are kind of small. So we took only for now. We took only 12 rows of the benchmark, and we added 4 attacks on each, so 12 by 4, 48. It's been a slow process because we're not able to rely on LLMs to do the inspection, so we had to do everything manually, slowly, and very painfully. And the 4 types of attacks that we use are needle injection, which adds an answer like a note or a comment near the relevant evidence. And because it's a benchmark, we know where the correct answers are because it's like highlighted to us, so we can make the attacks more reliably. We have state poisoning, which adds a summary, a revision note, or something like a table that can appear like an authoritative result. So imagine you have a non-technical engineer giving their opinions, which are for the most part not correct. And we have the forward and backward contradiction. They add like plausible update or corrections either later or earlier into the document. So this is for us to test if the position of the attacks or the mistakes change, if they're at the beginning or at the end, does it make any differences? So like, even though it doesn't use much context, if it's at the end, is it going to give more importance to the items at the end? And the last one is the strategic multi-answer. This changes how several candidates answer or ordering possibilities are presented. So most of the insertions, except the forward and backward, happen in the middle and or around the possible answers. So we try to keep it as natural as possible, and we do this, by asking an LLM. We use the ones that can hold a million contexts. So we give it the questions of the benchmark, the answers, and the highlighted part. So we don't give it the full thing because it's too big. They made too many mistakes. It cost us a lot of money. So yeah, we did this to create the attacks, and we're going to try to continue to have at least a good portion of the benchmark turned into a safety benchmark for us, or at least for a RAG use case. And then we evaluate on 2 very simple metrics. So we have the safety, which asks whether the final answer or anywhere in the answer adopts the injected claim. And we have the utility, which asks whether the system solves the tasks. And the utility counts even if the injected claim is somewhere in the trace. So it doesn't matter. If the answer is correct, we say the utility is high. So together, this describe our operating profile. We're also testing on, or at least planning to test on, multiple types of model families, and obviously try to incorporate more data sets if we can in the future, or when the paper and the code are submitted to a journal. And when they are, you're also going to be able to see the app. So it's a Gradio app, which will have this Explorer view that aligns those elements. You can see all of the trajectories where the injected claims are happening. It's going to be highlighted for you. And basically, if you want to create your own data set, whether you want to use it for safety of your own systems or for training, let's say a coding agent or updating it, this is how they do the annotation. So it's like a nice kind of easy annotation view. But I'll not talk too much or focus too much on this part. But if you want, we can come back to this during the questions. Instead, I'm going to focus on the 2 types of failures that we are finding for now. And we have classified them as translation-style failures and location-style failures. So the translation-style failures happens when the RLM search for exact tokens as the question or the answer like it thinks it's looking for. So then it finds nearby translations inside of the document, and then feeds everything into the source or the base LLM. Then these notes usually look very plausible and very much resemble the correct answer. Then the RLM retrieved those obviously the regions. It treats the injected claims as possible answers, and and then accept them as the 5 minutes. Okay, so it accepts them as correct answers when they are not. The second one is location-style failures, which are very simple if you think about them. We saw that when the attacks are at the end and at the beginning, they kind of work better, even if the attack is kind of stupid, to be honest. So yeah, I guess we can skip some parts to save some time. So the results, what we found. For now, we have found 4 types of results. The first one is, you can see it on the graphs. The other 3 are not on the graph. So the first one you can see now, for all of the attacks, they're always visible when you're using the LLM. So they're kind of all more or less succeeding. For the other one we found interesting was there is an LLM, a Queen 8 billion parameter model that was fine-tuned specifically for RLM use cases. So it's created by the author of the main paper of the RLM. So it knows how an RLM works. It's supposed to work best. So when we tested the base and root model or submodels with that, I guess, version, it had no poisoning, which you can see it in this graph, but it got 0 of the poisoning. So it never accepted any of the attacks, but the utility was horrible. So we got 40% utility, which means only 40% of the questions we answered correctly. But when we use GPT-5 as the root model and then smaller models as, I guess, the helper models, we got these attacks. So the bigger models were getting the attacks, but their utility was around 74%. So for me and for us, I think we saw this as maybe we haven't tested enough, so we probably have to do more testing to see whether maybe the small model is too small to be able to answer such difficult questions. Yeah. I guess, kind of skipping or summarizing some parts here. We did also some tests with Claude, and we did some by Anthropic models. We did GPT-5 Mini, GPT 5.6, 5.5. And what we found was when you're using the large models, the submodels, they don't matter much because all of them are making the same mistakes, the big models. And we found that the main mistakes are happening when the attacks are getting to the root model, and the root model is the one that's causing the mistakes, not the submodels. So you can work with large submodels or small submodels. If they're capable, they're all going to give you relatively the same results. And one more thing we did was actually fun. So we tested root goal and output schema reminders. So these were helper functions that would ask the RLM to, hey, double check your results. Is this correct? Does this make sense? Could there be an incorrect solution here or a claim here? And when we did this, our attack rates went down by 20%. But as you can guess, the utility cost went up by 50%, which meant it was looping almost endlessly on the task. And again, we find this a very possible solution, but we feel like we have to work on this a bit longer. Right, so where we are. I guess we don't have too much time left. So we can return to the main claim, which an RLMs can trust source errors and then it turn it into answers because it's doing the search, which finds a local plausible plan, and then it's putting everything into the state, which preserves or uses the conclusion as a for sure answer. And then the answer control, which is the final part, adopts the injected claim as evidence. So this is why we feel the source trajectory is very important. We also believe that this could be, at least this type of trajectory, checking every single step, can be very important into other non-RLM specific use cases. Like I mentioned, coding agents, the big companies, they always annotate their data using these steps. So they want to see where the mistake happened. They want to go through them step by step and try to put guardrails on them to prevent the mistakes without spending 50% more we have been doing. So this study is still limited and has some clear limits, but with some more work, hopefully in the next couple of months, we're going to be able to publish it. I guess the final conclusion here is that a useful design principle, the answer should earn its evidence. That's it. Thank you.
Thank you. I think we have 5 minutes for questions. So if you have questions, please wait. Yeah, I want to show you something.
Thank you for interesting talk and topic. When RLM approach it's not effective, which limit we have when try to apply a recursive language model reasoning?
The main limitations that we were looking into and finding was that these injections and the mistakes that can happen early on, they propagate like too easily, and by using the base RLM, it's not, I guess, enterprise ready, like, or for production ready, because it's making like some stupid and unnecessary mistakes.
Okay.
That's the main purpose of why we started this. Yeah. There was hype on Twitter, and people were recommending we use this, and we were like, we can't use it without testing first. So, yeah.
Okay, any other questions?
Thank you so much. Actually, you have mentioned related to metrics. What kind of metrics we should use to safety our model?
Sorry, can you repeat?
What kind of metrics actually it's necessary to safety our model?
Yeah.
The type of metrics.
So we have 2 types of metrics that we were using. One of them was to just check like whether the injections were included inside of the trajectory, and the second one was like which step it started and how it propagated over the next step. So if it started at the let's say somewhere in the middle, but then it didn't move forward, then we see this as a half success because it still like got it somewhere in the middle. And but of course, if it went all the way through into the final answer, then that's complete failure. Yeah.
Any other question? If no,
Great. Thank you.
Thank you.